Hello everyone, my name is Archana Devi. I am Assistant Professor from Rajagiri School of Engineering in Computer Science Department. So the topic that we are going to see in this video lecture is from the subject Computer System Architecture, which is a 7th semester BTech subject for CSC students. We will be covering the first topic in Module 2. In Module 2, the topics are covered from Chapter 4 in the textbook Advanced Computer Architecture prescribed for K2 students. So Chapter 4 contains these three sections which you will have to learn. In this we'll be seeing processors and memory hierarchy, where the first two section covers about processors and the last section discusses about memory hierarchy technology. So in this video lecture, we'll be covering the topics under 4.1 Advanced Processor Technology. These are the four sections which you have to learn under this section. So the major processor families can be classified as CISC, RISC, which you are already familiar. You would have heard about CISC and RISC architecture, right? Apart from that, you have other processor families like superscalar, VLIW, very long instruction word, super pipelined, vector, symbolic processors, and so on. So these are the major processor families which are covered in this section. And then the scalar and vector processors are normally used for numerical computations. Symbolic processors are mainly used for AI, artificial intelligence applications. So let's start with the first subsection in this topic, 4.1.1 design space of processors. So under design space of processors, the processor families are mainly mapped into a space of clock rate versus clock cycles per instruction. So any processor family if you take, we can have a comparison between the clock rate or the clock speed and the clock cycles per instruction, which is a CPI. So mostly processors of multi-core type, embedded, low cost, mainly low power consumption processors will be towards this side. Okay, so here you can see that the range of clock speed increases towards the right and the range of CPI increases towards top. So such type of low power performance processors will have lower clock rate, whereas high power performance processors will have higher clock rate. As you go towards the right, the performance will be increased. And in this diagram, they have mainly shown the classification for CISC and RISC processors. So as you can see, CISC processors has CPI starting from 2 onwards and it goes on. Whereas for RISC processor, the number of clock cycles per instruction is low. It's mostly between 1 and 2. And the clock speed, it varies, but normally CISC has fewer clock speed, whereas RISC processors will have more clock speed. So the clock rate is moved from low to high, and now the manufacturers are trying to lower the CPI rate. So the ultimate aim is to design a processor with lower CPI rate, because the clock cycles per instruction should be as low as possible to have better performance. So as shown in the previous diagram, the two dominant ones are RISC and CISC. So under the above categories, we have seen that the processors designed for following aims have lower clock speed, right? Multi-core chips, embedded applications, low-cost applications, and low power consumption processors applications. Then high-performance processors are mainly designed to operate at higher clock speeds. So for the design space of CISC and RISC, in CISC architecture, the clock rate ranges up to few gigahertz, whereas the CPI varies from 1 to 20. Some of the few prominent examples are Intel Pentium, x86 and M6 Motorola family. Okay. Then under RISC architecture, the design space it has more clock rate and the CPI is reduced between 1 and 2 clock cycles. Some of the prominent examples we have SPARC, Scalable Processor Architecture, MIPS, microprocessor without interlocked pipeline stages, ARM architecture, etc. Now if you look at instruction pipeline, let's understand what an instruction pipeline is. So the execution cycle of an instruction mainly involves 4 phases. So these phases can be 3, can be 4, 5 or 6 depending upon the processor. So if it is a 4 phases, then those phases can be categorized as instruction fetch, instruction decode, execution and write back. So the pipeline receives successive instructions from one end and it executes them in a streamlined, overlapped fashion. So some of the terminologies associated with instruction pipeline. One, we have pipeline cycle. So this pipeline cycle is the time required for each phase to complete its operation, assuming equal delay in all the phases. So what is the time required for each phase to complete its operation? That is pipeline cycle. So normally we'll have fixed clock cycle time for each phase. Variable clock cycle time is rarely used. Then instruction pipeline cycle is the clock period of the instruction pipeline. What is the clock period of the instruction or the clock rate of the instruction pipeline? That is instruction pipeline cycle. Then instruction issue latency, the time required between the issue of two adjacent instructions. That is you are pushing the instructions into pipeline, right? So what is the time between the issue of two adjacent instructions? That is instruction issue latency. Then instruction issue rate, the number of instructions issued per cycle. In a particular cycle, how many instructions can you issue in a clock cycle? Normally it will be 1, but there are cases where we can issue more than 1 instruction. That is instruction issue rate. Then another terminology associated with pipeline, simple operation latency. That is how many clock cycles are needed to perform simple operations like integer additions, load, store, branch, move, etc. So how many clock cycles will be needed to perform such operations? You call it as simple operation latency. Resource conflicts. So there can arise a case where we can have a resource conflict between 2 or more instructions. That is, if 2 or more instruction requires the same functional unit at the same time. Say both the functions are trying to access memory at the same time, or both 2 or more instructions are trying to access register at the same time, or ALU at the same time. All those are called as resource conflicts. So now these are some of the cases where we can have pipeline execution. The first case is the standard one where each of the phase will be executed in a clock cycle. So the first instruction is pushed to pipeline, and when the second instruction is being decoded, the second instruction, when the first instruction is being decoded, the second instruction is being pushed to pipeline, and it goes on. So in every one clock cycle, one instruction is being issued. So each stage takes one clock cycle. Then, so what happens here? The CPI, the average CPI becomes 1 because from the fourth time onwards, here after the completion of every time, every second, one instruction is getting executed. One instruction is being it's completing its execution, right? So the clock cycles will per instruction will become 1 in this case. Now the second case is where 2 clock cycles, only after 2 clock cycles, the next instruction is being pushed to pipeline. So again, these 2 instruction gets instruction fetch and decode, and then when the first instruction is being executed, execution is over, the third instruction is being pushed to pipeline. In the first case, when the first instruction was already in execution stage, the third instruction was pushed to pipeline. So here it gets delayed. So the successive instructions is being pushed to pipeline after 2 clock cycles. So you will have a CPI of 2 in this case. So this is an under pipelined with 2 cycles per instruction issue. Two cycles per instruction issue. Now this performance of such pipeline processor will be low. Now another rare case is the 2 stages, instruction and fetch is being combined into a single stage, and execution and write back is being combined into a single stage. So here both the stages takes 2 clock cycle. So the base cycle becomes the clock cycle becomes twice the base cycle. So the only difference is the two stages are being combined together into a single stage. And this entire clock cycle, both the stages complete, gets executed, gets finished. Okay, so for this case also you'll have poor performance. Normally this is a normal pipeline case in which we can achieve high performance. So now let us look at the next section, instruction set architectures. So any instruction set architecture that you take, um, it will it will mainly fall into two category. So before that, let's see what instruction set is. They are machine instructions that a programmer can use while programming the machine. What are the different types of instructions that the system can use, that a programmer can use while programming the machine? So the complexity of an instruction, when you talk about an instruction, it depends on various factors like instruction format, whether there is a single instruction format or multiple formats, data format, in which all ways can you represent the data, integers, floating point, characters, the various addressing modes. Some processor supports very few addressing modes, whereas some processor supports more addressing modes. Then the count of general purpose registers, the opcode specifications, in which all way can you specify the instructions. So all flow control mechanism, in which all ways data can flow between the instructions. So all these are factors that affects the complexity of an instruction. So based on this, any instruction set architecture can be categorized into two: complex instruction set and reduced instruction set. So this, we are already familiar with these two, CISC architecture and RISC architecture. Any processor you take, they will fall under any of these two categories. So let's start with a complex instruction set. Let's look at the common features of CISC architecture. Normally you will have 120 to 350 instructions in CISC, complex instructions. Then in CISC, variable instruction format and data formats is supported. You can have say 32-bit instruction length, variable instruction format. So it can, one format can be there, another format can be there which is of different length, which supports various types of data. Due to that, you will have variable length instructions. Now talking about general purpose registers, normally in any CISC you will have a count varying from 8 to 24, which is a small set. Then it executes large number of memory reference operations. It mainly executes memory reference operations. Any operation, say add a comma b, so the operands are fetched from memory and the calculation is made and the result is returned back to the memory directly. So this makes the system slower because you are accessing the memory directly. Now it supports more addressing modes. The addressing mode supported in CISC is much more compared to RISC. It has, as we have mentioned earlier, it has less clock rate compared to RISC architecture. So these are some of the basic features of CISC architecture. Now talking about RISC, reduced instruction set architecture, RISC features. So it has less number of instructions in reduced instruction set, whereas you have a fixed instruction format. Normally it will be of 32 bits, but it can vary. Number of addressing modes is reduced. Since you have a fixed instruction format, you cannot have more addressing modes. Then most instructions are register based. That is, you do all the operations inside registers. If you want to perform any operation, then the operands have to be fetched from memory, stored in register using load and store operations, and the arithmetic and logic operations are performed in registers itself. So this makes the processor faster because the operations are performed inside the values contained in registers. So the memory access, as I mentioned, is done by load and store instructions only. And most of the instructions gets executed in a single clock cycle. Here hardwired control is used. So in CISC architecture, one point which was missed out, microprogrammed control is used. So microprogrammed control, which we will see in the diagram that comes, then it has, as mentioned, reduced instruction set architecture has higher clock rate and lower CPI, around 1 to 2. Then since like we can achieve higher performance in reduced instruction set architecture because you have less number of instructions being executed, and we have hardware control which is used. So because of all these factors, performance can be you'll have better performance. So in a nutshell, it's all tabulated, the main differences between RISC and CISC architecture. So this talks about the instruction size set and the instruction format. So under CISC, you have large number of instructions with variable formats, but in reduced instruction set, you have small set of instructions. Then the addressing modes is more in CISC architecture. In RISC, it is reduced, limited. General purpose registers is less in the case of CISC architecture, whereas in the case of RISC architecture, you have more numbers. CPI is more for CISC, whereas it is less in reduced RISC. So the CPU control is micro-coded in microprogram memory, whereas in reduced instruction set architecture, it is hardwired. That we'll see in the diagram. So now I also given a reference for the comparison between RISC and CISC architecture. So this is the architectural distinction between CISC and RISC architecture. So under CISC, you can see you have a memory, a common memory for both instruction and data, and you have a cache, a single cache, which takes both instruction as well as data, and the path for instruction and data is the same to the control unit. So through the same bus, both instruction and data flows to the control unit. So in this case, the control signals associated with the operations are stored inside the microprogrammed control memory. So every time the control unit wants to send a signal, those operations are fetched from microprogrammed control memory, and based on that, the instruction on data will be fetched from memory through cache. So that makes the system slower in the case of CISC architecture. Now in RISC architecture, you have the instruction and data being taken out in separate caches. So you have a separate cache, a split instruction cache and a data cache. So hence it has the data and instruction flows in separate buses. So the data path is different for both instruction and data, and they both go to a hardwired control unit. So in hardwired control unit, there are fixed logic circuits being wired inside the control unit itself. So this makes the operations faster. You don't have to depend upon a separate memory in order to issue the control signals. Everything is wired inside the control unit itself. That makes the RISC processor faster. So in CISC architecture, you have a microprogrammed control with unified cache, a single cache. Whereas in RISC architecture, you have two separate caches. So that's about the instruction set architecture. Now let us look at the section 4.1.3, CISC scalar processors. So under CISC scalar processor, let's see what a scalar processor is. A scalar processor executes scalar data. That is a single instruction. It can execute only a single instruction, scalar processor. Now, what is simplest scalar processor? It executes integer instruction using fixed point operands. Using fixed point operands, the integer instructions are being executed. It cannot have floating point real values. Capable scalar processor can execute both integer as well as floating point operations. Whereas modern scalar processor it possesses both integer unit and floating point unit. Separate integer unit to execute integer instructions operations, and separate floating point unit to execute floating point operations. So some of the common CISC representative architectures are VAX 8600, Motorola MC68040, Intel i486. Out of this, we'll learn these two architectures. VAX. So first let's start with VAX 8600. So let us look at some of the main features of this architecture. It was introduced by Digital Equipment Corporation. It uses microprogrammed control unit, which we have already seen. Then altogether it supports 300 instructions, and it has 20 addressing modes. Then the number of general purpose registers are 16. The CPI ranges from 2 to 20 clock cycles, and CPU mainly has two functional units, one execution unit and a floating point unit, and it is used for concurrent execution of both integer and floating point instructions. That is why you have separate execution unit which takes care of integer operating instructions, and another floating point unit which takes care of floating point operations. So these are the important features of VAX 8600 architecture, and it has a unified cache for holding both data and instruction, a single cache for holding both data and instruction. Now in this architecture, pipelining takes altogether 6 stages. Then there is another instruction unit. So this instruction unit prefetches and decodes instructions. It handles branching operations, and it also supplies operands to the two functional units inside the processor, where we have the execution unit and floating point unit. So to those two units, instruction unit only supplies the operands in a pipelined manner. Then we have a translation look aside buffer also, TLB. It's mainly used for the conversion of physical address, right? Physical address to virtual address. So this is used in memory control for the fast generation of physical address from virtual address. So this is an architecture diagram for VAX 8600 architecture. So here we can see there is an execution unit. Then there is a floating point unit. So this is the instruction unit which fetches the instructions from memory. So when it fetches the instruction from memory, this fast TLB is used, from which it goes to cache, right? And the instruction unit fetches the instruction, decodes it, and if it's an integer operation, it's fed to integer unit. If it's a floating point operation, it's fed to floating point unit. So this is a general idea for the VAX 8600 architecture. Now let us look at Motorola MC68040 architecture. So let us look at some of the core features of this architecture. It mainly consists of 1.2 million transistors with fewer instructions compared to VAX architecture, and fewer general purpose registers, 16 general purpose registers, 18 addressing modes. Then in this, it's not a unified cache. We have separate instruction and data cache with 4 kilobytes instruction cache and 4 kilobyte data cache. And we also have separate memory management unit which is supported by ATC, which is address translation cache. This is equivalent to your TLB only, translation look aside buffer. So we have separate memory management unit for both data and instructions in the case of Motorola architecture. And the data format ranges from 8 to 80 bits. That much range of data format is supported in Motorola. Now in this, the processor has two units. Again, just like we had in VAX architecture, here also we have two units, integer unit and the floating point unit. So the difference is the number of pipeline stages for integer unit and floating point unit is different. In integer unit, we have 6-stage instruction pipeline, and whereas in floating point unit, it's only 3-stage pipeline. So all the instructions are decoded in integer unit, and if it's a floating point instruction, it is forwarded to the floating point unit for execution. That is why the number of stages in floating point unit is reduced. Now, as we said before, the memory management unit has separate memory for data and instruction. So since there is separate memory for data and instruction, you need separate bus for instruction and data, both 32-bit wide. And each of the two cache for data cache and instruction cache, it has altogether 64 entries for TLB. So that provides fast translation from virtual to physical address. So now this is the architecture for the Motorola processor. So here you can see this is a floating point unit and integer unit. So as we have said, integer unit has 6 pipeline stages: instruction fetch, decode, effective address calculation, effective address fetch, execute and write back. Whereas floating point unit has only three stages: convert, execute and write back. And this is a instruction memory unit, and this is a data memory unit. So both has separate controller, and both has separate cache as well. With the help of ATC, it achieves the conversion of virtual address and physical address. So you have separate bus for instruction and address data also, each 32-bit wide. So this is a architecture diagram of Motorola processor. Now some of the common CISC Motorola microprocessor families, we have Intel family and Motorola family. So these are some of the popular ones with its bit specification. Now let us look at the last section, 4.1.4, RISC scalar processor. So here we'll see some of the popular RISC scalar processor. So this generic RISC processors are also called as scalar RISC processor. They are designed to issue only one instructions per cycle, whereas in CISC, in a single clock cycle, multiple instructions are being executed. So here, in order to achieve this, we need a good compiler to achieve a better performance, in RISC compared to CISC. So some of RISC representatives, we have SPARC, which is a scalable processor architecture, Intel i860 and Motorola M88100. So here all of these processors listed here uses 32-bit instructions. So I hope you recollect, RISC takes fixed length instructions, right? So for these processors, it is 32 bits. Let us look at SunSpark architecture and Intel i860 under the RISC representatives. So let's start with SunSpark. So SunSpark architecture is implemented by a number of licensed manufacturers. All of them implemented floating point unit on a separate coprocessor chip. So SunSpark instruction set has 69 basic instructions, and it runs each procedure, a set of instruction, using 32-bit registers. So 32-bit registers are there. So out of this 32-bit, 8 of the registers are globally shared across the procedures, and the remaining 24 are called as window registers, which is associated with only one dedicated procedure. So for each dedicated procedure, 24 registers will be associated, and the remaining 8 can be globally shared across all the procedures. So this is about SunSpark. Now let us look at Intel i860 architecture. So in Intel i860, it's a 64-bit RISC processor which is fabricated on a single chip. This executes only 82 instructions, with 42 instructions categorized as integer, 24 categorized as floating point, and 10 categorized as graphics instructions, and 6 categorized as assembler pseudo operations. So all instructions are executed in one clock cycle only. Some of the application of this processor, we can use it in floating point accelerator, graphics subsystem because it supports graphical instructions, then workstations, multiprocessors, multi-computers. So when you take the architecture of Intel i860, there are 9 functional units altogether. The first one, bus control unit. So all the units are listed here: data cache, instruction cache, memory management unit, integer unit, floating point control unit, pipeline adder unit, pipeline multiplier unit, and graphics unit. And we also have a major unit along with graphics unit that we'll see. So all these units are interconnected using multiple data path. So the range of this data path, the bandwidth of this data path ranges from 32 to 128 bits. So let us look at all these functional units one by one. Bus control unit. So we have external and internal buses, right? External buses mainly used to connect to the external devices in the measure system, like your keyboard, I/O devices, or USB, and so on. And internal buses will be used for internal communication within the processor, memory, and so on. So in the case of this architecture, your external and internal address bus will be of 32 bits wide, whereas external and internal data bus will be of 64 bits wide. Then the instruction cache, the size is usually 4 kilobytes and it is organized as a two-way set associative memory. So that there are different ways in which we can organize cache, right? So you'd have heard of direct mapping, set associative mapping. So here it is two-way set associative. And the block size in cache is 32 bytes and it can transfer 64 bits per clock cycle. In every clock cycle it can transfer data of around 64 bits. It's an instruction, not data. Then talking about data cache. So the size of data cache is 8 kilobytes and it's implemented. This is also implemented using two-way set associative and it can transfer 128 bits per clock cycle. Data can be transferred 128 bits per clock cycle and the write back policy is used in data cache. So there are different methods in which you can write a data, right, in cache as well as in memory. So the write back policy is used in data cache. Memory management unit is implemented using a 4 kilobyte paged virtual memory using via translation look aside buffer. Now the integer unit is of 32 bits and it can execute load, store, integer bit control instructions. So it fetches instructions for floating point control unit. This unit also fetches instructions for floating point control unit. Now inside floating point control unit we have two separate units for multiplication and added. So both these can be used separately or simultaneously. It's controlled by a floating point control unit and the dual operation floating point instructions use both adder and multiplier units in parallel. That's why you have two separate units. There's a separate graphics unit which can execute integer operations corresponding to 8, 16 or 32-bit pixel data types. This supports 3D drawing in graphics frame buffer and it also supports color intensity, shading, hidden surface elimination and so on. Now the merge register is used only for vector integer instructions. So this register will accumulate the result of multiple addition operations, say in the case of an array. So this is the overall architecture of this i86 processor. So the different units you can see here: instruction cache, memory management unit, data cache, bus control unit, integer unit, floating point unit, graphics unit and merge register is in a single unit, pipelined adder unit and the multiplier unit. So all these are interconnected using different buses. So this is an overall structure of Intel i86 RISC processor. So with that we have come to the end of this video lecture where we have seen the topics covered in 4.1 Advanced Processor Technology. So now in the next series of video lecture you will be learning about superscalar vector processor and memory hierarchy technology. Thank you so much.